Since it is recorded, I will talk in English again. All right. So I'm going to be talking about example number 3.1 in our textbook. And in here, let's say you have a lake. The volume of the lake is 50,000 kilometers. And let's say this one follows the first order reaction. What is first order reaction? And we said if my n is 1 in here, this is my first order reaction. Okay? And when we set up mass balance equation, we will talk about mass due to movement of water and dispersion of water and decay, right? In this case, this is decay. If we multiply void in here, and we are going to talk about mass per time due to reaction. So, this time, this is the situation, okay? I have a Q, I have a C, Q times C coming in. Also, I have another Q and another C coming in. If we multiply it together, if I express this with mass per time, this is 50,000 grams per day or 50 kilograms per day. This is input 1. Input 2, 2,500 kilometers per day and 30 milligrams per liter. If you multiply them together, this is 75 kilo. Okay? And I have this volume. And then my question is, what is your concentration? Okay? In this case, I will assume my lake is just completely mixed. Let's say you have some kind of propeller inside, always moving in. So you have concentration just mixed right away. And also, we will also assume we will have a steady state. We are not going to talk about time. And dynamic means if you have C and T, that's dynamic. It's about time, right? It keeps changing. But in this case, we are not going to talk about T at all. Okay? We will talk about that later. But in this case, we'll just assume this one was just mixed right away, and somehow decomposition or reaction that occurred in that flash moment. So everything is completed in that period. Then I have some kind of concentration here. Also, I will assume the concentration inside and right at this point is the same. When I have not draw an arrow, I will always talk about concentration right at the point which is departing or exceeding from your lake. Okay? So at that really point. So since I said everywhere in here has the same concentration, and this must be same as concentration anywhere inside of. Well, that's just assumption. We'll just assume like that. That's not your situation, right, at all. Since in reality, concentration here, there, and then all of them are going to be different. But we'll just assume, we'll just make our situation simpler so that we can do some kind of scientific analysis. Well, okay, I know Q1 and I know Q2. So I just naturally know my new Q is going to be, the summation was 2. Q1 plus Q2 is my new Q. Simple, right? And then we studied that our new Q is going to be the weighting factor, weighted average of those two is my concentration. If we don't talk about the reaction, that's the right answer. But this time, I have a decay. Then my question is, what is your concentration? Okay? But we'll just solve this problem step by step. Okay. Then I have 2 mass per time. 1 and 2 is going to be my 50, 75. Then I have 125 is my mass per time. Total mass per time coming into here. And if I don't have anything, okay, this is 125 kilogram per day, and this is 7,500 cubic meter per day. And then since this one is kind of imaginary Q and imaginary C, and then if we simply use these two to calculate nu, then we can divide 125 with 7,500. Then this is 16.7 is going to be weighted average of these two. In this case, we are not talking about K. Okay, simple mixing, right? Only. Okay. Then this is so-called as CSTR, continuously stirred tank reactor, and this kind of reactor is very often used in our treatment system. So in other words, we will just, even though there is nothing like this, we'll assume there's an imaginary kind of stir or the fan that completely mixes your system. So imaginary system is like that. And you have something coming in, there's something going out, and we can have some reaction. As also, because of its weight, they can settle to the bottom. So in here, we'll have this one is this one, that is that, and this one is that, and this one is that. So simply, something coming in is plus, something going out is minus. That is what is left in here. Okay? If you have 10, you have 1, 2, 3, 10 minus 1, minus 2, minus 3, which is 4, and that is inside. That must be in here. Right? Okay. And the sad part about lecturing in English, and your face is not moving at all. It's not interesting at all to me. Sometimes sad. Anyway, so but I want to change my situation into a form of equation so that I can calculate easily. Okay, I know that my loading can be W, or sometimes if I can divide them into flow rate and concentration, that can be Q times C. Outflow can be Q times C. Reaction, I have C, K and C, right? But if I know volume, if I multiply by volume, then I have mass per time. And just focus on minus. And my settling can be V times A times C. I will talk about that later. Anyway, this is mass per time. Anyway, and my total balance, actually this was dm dt, but dm dt, and m is V times C. According to the chain rule, I can write this like this. And in this case, to make our life easier, I will assume my volume of the system is constant. If you differentiate your constant, you will get what? 0. So when I say V dc dt like this, I obviously am neglecting this part. If your system has changing volume, you cannot use this one. But in this case, as a kind of introduction of the work about modeling, I will just use the simplest case. So that's why I want to assume this one is 0. But in general, this one does not happen. In general, does not happen at all. Okay? But you will have to make a decision. In some case, can we neglect this one or not? But that's your depend on that's part of function of your experience and database that you have. Okay, so then this is mass balance. dMdt equals my input, output 1, output 2, output 3. Output 1, output 2, output 3. Right? Okay. So if I set up equation like this, then I have some choice that I can calculate. And if I know terms, then we can just grade those. And then if I want to calculate C, then I can just move everything to the right hand side and then do something about it. Okay? Alright. And in here, the mass per time due to reaction, as I expressed in here, is like V dCdt due to reaction is case CV. If we disregard those two, we can tell, okay, that was my expression for the reaction. But originally, as I said, I should have the V, because that actually started from here. And in here, I usually talk about this inside of my tank. And that tank usually has fixed volume. Then in that case, the dVdt is 0. V dCdt actually is something, but since I know V, it is in general, that we just omit V. But in reality, we need to have this one. Okay. And this one was not from theory, as I said. This is different. And if you are talking about the Newton's second law, that's F equals NA. That's kind of theory, even though there was observed. But if you know A, if you M, you will have exactly the value F. But in here, if you know C, if you know K, you are not going to have exact dCdt, because it's kind of empirical equation. Based on your experimental data, you may have error. Okay? So again, this accelerating velocity, this equation is also empirical equation. Well, free dCdt, again, will be, the unit of that one will be mass per time. Right? That's mass per time. And then, as I said in here, this is the expression that I use when I want to talk about reaction. But if I want to talk about this Rxn, and V dCdt settling, then I would say, okay, like this. And since those are empirical equations, I don't really need to explain too much. But also, since they are new to all of you, I'll explain it a little bit. And actually this is minus as well. And when we talk about settling and movement of particle from a certain height to another height. Okay? So we are going to talk about how fast it is going to, usually we will have subscript S. It is going to move. Okay? And then we're going to have a number of particles inside. And that is going to be the function of concentration. And then that is going to be dependent on your whole area. So if we think about though there was a little knife, I will use that. And we know they have those kind of unit system, and then if we can cancel those, what do we have? Mass per time, right? So these two, and if we rearrange this one, minus KVC, this one and this one, they have very similar function, role. One is about volume, whole volume, okay? And my reaction occurs in whole volume, that means. But my settling occurs in the whole area, and they settle together, like that. They have that kind of difference. Okay? So, in other words, it's not going to be wrong if you express this like KSVC. If you have some kind of settling reaction, it's not right. But, if you can say like that, it's okay. It's okay. But if we say like this, and we cannot really differentiate, we cannot overlay the physical meaning, and so we'll just differentiate them a little bit. The settling is about the whole area. That's a lot easier for us to imagine. And then, or visualize. And this reaction is about whole volume. That's the difference. Right? So, in here, KV, VSA, they have the same meaning. If I somehow make it those two the same, and what's the meaning of it? In the VS, in here, the A can be in the denominator right here. And then V is my volume, then V is what? A times H, right? My A times H is your volume. Just like that. Then if I divide my V with A, then I have H. So between reaction rate and settling velocity, it has that kind of meaning. That's why I told you we can express my settling like first order. But this is just mathematical this and that. So physically it doesn't mean anything. But mathematically we can just say like that, but that's just mathematical equation only. Alright? Practice box number 3.1. And this one says, okay, box number 3.1. Let's go back to our textbook. Box. In Steele's box, there are a lot of good stuff. Page 51. We have box 3.1. Parameterization. Okay? So it talks about your reaction and settling velocity, and he talks about, write this one. Your settling velocity can be analyzed using the concept of reaction rate. So if you just use your memory, imagination a little bit, and then it's going to be better for you to understand what's going on. So mathematically, really doesn't mean, because K, if you know K and V, if you know Vs and A, and those are mathematically the value can be the same. But many times you want to differentiate them because settling is about particulate matter. Decay is about dissolved and particulate matter. Particulate means you have a particle and it doesn't dissolve. It has some physical shape. Dissolve means you don't see it. You may see color, but they are just moving like water inside. So they have chemically also different entity. Settling usually is about soil or the heavy metal, and they can provide kind of a surface. There's some other material can be attached or detached or observed or deserved, right? So they have different meaning. So I want you to understand the difference of these two physical meanings of those two, even though they can be interpreted mathematically like this, but very much important. So I want you to read carefully over 3.1 again, not now, because some good student you may have read it already. 천진 뭐 읽어봤지? 예습해서 이거 친구하고. Thank you. 예습해도 하나도 뭐라 김영란법에 안 걸리니까. 알겠습니까? 예습해서 남줍니까? 여러분도 다 가집니다. Okay. And Steve Shepard, he is a good writer. He's very nice, and he writes wrote his textbook in a very nice way, so you can understand easily. So I like his writing way of writing. So read them, and it's going to be good for your modeling and the others as well. Okay. So what is important? This one says, okay, this one, if you can use this one, that one, but what is the base of selection? That's representing the process that being modeled. And one is about settling, the other is about decay. So there are the different processes, right? Okay, then we're going to get back to example 3.1 again. And then, now, okay, 3.1 again. Same problem. 75, I just moved 75 to here. And 50. And then, I don't know, somehow, my decay can be, let's say, I was able to calculate my decay, and that was happened to be 100. And then my Q will be Q1 plus Q2, which is 7,500. And my W in this case, 50 plus 75, and decay was 100. And then I know my remaining mass per time is going to be 25 kilograms per day. And then I can calculate my concentration by using these two numbers, and so 25 divided by 7,500 is going to be 3.3. What was that value before? 16.7. Right? Do you remember? Without reaction, it was 16.7. No? Yes? And now with reaction, 3.3. What does that mean? This one, this lake, did some work to reduce your concentration. And if this is your detention pond, this can be some kind of buffer zone between your source of problem and your water. And if you make it stay there for a while, and then you were able to reduce your concentration from 16.7 to 3.3, which is really big, which is very good. for your river and lake, because reduced concentration is going to be transferred. So we still, okay, we have this one. I'm going to be talking about same stuff again and again. In this case, let's say, okay, I have somehow this much coming in. Maybe, am I going to talk about same, I don't care. Okay, I have this much flow, let's say. I have this much concentration coming in. And I had some wastewater treatment plant coming in like this. And if there is air flux, okay, now we have flux here. When you talk about flux, what is it? Mass per area per time. And if I know area, then I can calculate mass per time. So in here, I simply need to know this area, right? Then I will just multiply this area, then I will calculate some input from the air. What is the area? I know volume, I know H. Then V divided by H is my A. Then I can simply calculate the loading coming in from the air. Actually, this is going to be very important nowadays. In your city, if you have a lot of vehicles, a lot of cars, then they can make a lot of dust. And that can react like a colloidal material in your water. That doesn't settle it easily at all. So they can move to your water and then act as a pollutant source. Also, yellow dust from China. Since it's recorded, I should be careful. Anyway, yellow dust comes from China, and that can have a lot of heavy metal, a lot of something, a lot of this and that. Since they are a little bit heavier than the air, they can freely move and can transport it to our country as well. But they can land on to our lake, to river, and then provide the source of the pollution. That can be either heavy metal or phosphorus and whatsoever. So this can be very much important. One of the non-point source. All right. Steady-state concentration of the lake. And mass. Let's check about mass. Okay. And here, actually, we did it. And in here, let's say we have another W is W1, W2, W3, and this is W. Anyway, 1, 2, 3, and I think 4 is the decay. Since I played this one a little bit recently, and I messed things a little bit. Well, then anyway, let's assume we have an inflow. Which is 75 times concentration 10, Q times C, and air is J was the flux, and then if I know AS, and then this is the volume divided by H, right? So I could calculate the loading from the air, factoring, and it was 50 kilo per day, and it was just given. So we just know. And for the factory, usually they may have very, very high concentration, but flow can be really small. In that case, if you would just disregard the Q, but mass can be very high. In that case, your mass per time is one of the way that you express as loading input. So if we add all of them together, and then Q plus KV, we'll talk about that. And then your concentration is going to be 5957. And we have now 3 different concentrations, 6.7, 3.3, and 597. Obviously, because we have more input from somewhere else, this one became higher. Okay? And so then they just go on, and we will just think about what is the Q flowing out, which is then I don't think we have anything significant Q coming in from factory and air. Then your Q is going to be the same as before. And if you know your concentration in here, if we multiply it together, that's your output mass per time. And the reaction in here, I said K times C times V is your reaction. And if you know K, if you know C, if you know V, then you can calculate. So if we divide my input like that and output like that, and the 53%, 54% is coming from inflow, and 36% is coming from the factory, and about 11% is coming from the air. Usually, it's going to be very difficult to control this, unless you have really big umbrella for your entire lake. That's impossible, right? Or we have to ask China to reduce it. And it's going to be also very difficult to control your just total flow. If this is too big. If this is your river, can you treat your river all the time? No. Very difficult. And it has to happen from your very upstream area, okay? And step by step. So in this case, maybe the only choice for you is to ask this guy to reduce your load, okay? And then you can tell how much in practice can really reduce our load. That kind of estimation is possible, right? And then also, if we subdivide our system, outflow is kind of 32% of the whole mass, and we were able to remove 68% of the mass that came in to this system. So this one removed 2/3 of the whole mass by reaction in here. So that can be our analysis about total system. So then I will just talk about steady state concentration. And we in here, I have not talked about this yet, but let's collect my equation. dm dt equals v dc dt and c dv dt. In this case, I will ignore that part. So in general, I would write this equation like that, and I have something coming in, something, let's say, and then mass in, right? And mass out, which is Q out and C. Also, I have a Q. I have a mass per time due to my reaction. I have a mass per time due to my settling time. And in the first phase of this class, I said we are going to talk about steady state. This, I said, I will not talk about time. Regardless of time, that means my concentration is going to be regardless of time. It's going to be constant. no matter what the time is, time 0, time infinity, time 10, 100, whatever it will be, my concentration is all the same. In this case, then my dc dt is how much? 절진. If you differentiate constant, what you will get? 상수 미분하면 yeah. Okay. Thank you. So, if this is 0, what you will get? V times 0 is 0. And let's say this whole thing can be expressed with big W, right? Like this. Then what is your C? Right there. Right? It's a matter of elementary school calculation like this. So this is your steady state concentration. Well, if we take a look at this equation more closely, then we can say, okay, something that makes its denominator larger is Q. If I have bigger Q, I have a smaller C. If I have bigger KC, then I have a smaller C. If I bigger Vs times A, then I have smaller C. What is it? What does that mean? If I remove more due to reaction, if I remove more due to settling, then I can have a smaller, because this one is bigger, my C is going to be smaller, right? Obviously, it's going to be easier if we make this one smaller, then also we can have a smaller C. And this W usually can be expressed Q times C. So in this case, we can either reduce C in or reduce Q, but reducing Q is not wise because Q also is in here as well. Okay? So divide by A in this textbook is called as assimilation factor, but I don't care. You can call whatever. Okay? Reducing factor, assimilation factor. Okay. So in here we'll talk about these later. But so far, if we talk about completely mixed system, you have a tank, something coming in, something going out, and then something coming in, something going out, something happens inside, and if you reach a steady state, that means it doesn't matter, it is not functional time anyway. Then you can say it's a 0, and then it's very easy to calculate concentration. Equilibrium concentration. Steady state concentration can be the same as equilibrium concentration. Physically, it means at time infinity, if you just let it go for a really long time, then you will anyway reach kind of state. That doesn't change at all. Actually, this steady state means, in reality, we always have some kind of changes. And let me just write a little bit this way. If you spend really long enough time from here, let's say I will say from T infinity, from here I will have constant. Then this is steady state. And this is dynamic state or non-state. Right? So if I say steady state, we don't care about here, right, at this time. Okay, we'll only talk about here, and we just assume this one just happened just in a very flash moment. Okay. All right. PDF. If you know this concept now, and the flow rate later, and flow with this burden a little more later, is going to be another piece of cake too. All right. So we talked about that, a transfer function, and still want to call it as the ratio between the input, output, and input is going to be like that, and then this is kind of C0 over C, and this is initial concentration, input concentration and output concentration, and this kind of efficiency or remover the rate of your system can be defined as beta. And if we add the settling effect, and we can say in addition to Kv, my V times As can be part of the denominator as well. We know that. And then it's okay. And it wants you to say what is a transfer function. In other words, what is your alpha and beta? And I think we can calculate them. So I will just leave you to play with those. Okay? So inflow concentration was, if we say, if you know dW and if you know Q, and then that's inflow concentration. Transfer concentration is the ratio between output and input, and this is 0.32. Residence time. Oh, that is very important. Residence time. Residence time. Residence time is the time that my particle water stay in your system. Okay? And actually water is molecule, right? Like a Mickey Mouse, 2H and O, 1 O and 2H. That's your water. And actually you have so many Mickey Mouse inside, attached together. Okay? So each particle of water have a time that actually stay in the system. And if there is V, and if you have Q, usually when you just let this one flow out, let's say, we'll just do this one. No, I think it's, we are going to talk about average residence time. Once something is coming in and it will just travel along, and then somehow, let's say, it'll get out from here. So each particle will follow, we just assume, each particle will follow the same path. Okay? So they will spend some time and then go. What does that mean? And it's like it takes some time for this water to fill this tank up, right? This is your residence time. And then if this one is full, and then you start to have a outflow. Okay? So then how much does it take? So that's your time, and then that is defined as like this. Actually, it's very natural that what is Q? Q is the mass of mass of water. Mass of water. Let's say like this. In a given time, because we can tell from the unit and by the definition, and my flow rate can be defined as cubic meter per second. In that case, cubic meter is volume, second in time. So if we just change t and q, and this is going to be your second. What is it? That is the time that satisfies this relationship. In other words, this is time that is necessary to make this volume full. Okay? So that can be regarded as a time that a little particle stay inside the system. That's your resonance time. Right? So resonance time definition is V divided by Q is your resonance time. But pollutant resonance time is different. I hope you learned this from wastewater engineering class, right? 이거 배웠죠? 오염물질 처리 시간. If you don't know this, you better go back to your textbook and read it over, because it's going to be on your exam. 기사 시험이나 어떤 일 다 나옵니다. Well, definition of pollutant. That is the actually this is the water resonance time. Actually, this is output of outflow. Outflow and what is in the system. And the resonance time of the pollutant is water system and outflow rate. Volume maybe better expression there, but and we know Q is the outflow and KV was the output somehow due to reaction in this case. And if you know this outflow, then this is going to be your resonance time for your pollutant. So go back to your textbook and then find it. I don't think I have really enough time to cover that. Okay, then what is dynamic? Dynamic means I want to know time when my concentration is going to reach at a certain point. And then I want to calculate time. In this case, I have to think about T. And then I cannot make my dCdt as 0. So dCdt will be there in my equation. That means I have to integrate, right? I have to integrate. I have to use a little better way to calculate my concentration. And then what is shape? Shape means this one can be linear or the curve. It's going to be faster or slower, like that. So, and if you have the function, if you can solve the equation, then you will be able to tell. Okay? All right. Then in here, I have W, QC, KCV, and VAC. This settling, reaction, output, loading. And if I divide everything by my V, I can get like that. Okay? And then I have a dCdt, and I will just move everything with C to here. And my V divided by V will be there. And my lambda is Q divided by V, K, and V divided by H. So anyway, this is going to be your constant, right? Just value. Then, if we can solve this equation, then we will be able to tell what is the concentration in a given time. And how to solve this one? Just piece of cake. Piece of cake. It's very easy. I will let you know. But I think time is up. So this is eigenvalue problem. But we can, I can talk about that when we cover chapter 4. So at this time, we're just moving through. And when you have a faster solution, faster reaction, then your curve is going to be like this. But if you have slow reaction, then your curve is going to move like that. And how many slides do I have? I covered already 24, but I think I'm almost done. Even though I didn't cover the rest of the slide, actually, yeah. Okay. Right. And let me just go on, just one more slide, maybe two more. And no, I'll stop here. I'll stop here because we need to explain a little bit more. Okay, 일단 끄고.